Welcome to this webinar on why some data analytics project succeeds and other fails. Yeah, I already peeked into the registration list and I see that today we have a very wide variety of people in the audience, of many different industries. The plan is to start with a very short introduction, only a few minutes, about IPCOS for people who don't know us, and then I will introduce the speaker of today, and then I will hand over the microphone to him. Christophe will present during about 40 to 45 minutes, and then we have time for questions from the audience. And the idea is that you ask your questions via the chat box. So you cannot use your microphone, just use your chat box to raise your questions. I will collect them, and then later on, after the presentation, I will ask them one by one to the speaker. Yeah. But you can already start asking your questions during the presentation. You do not have to wait until Christophe has finished. Good. Let me briefly introduce IPCOS in a couple of minutes only to you. IPCOS is a company is already active 27 years in the process industry. And process industry for us means upstream oil and gas processing, refining, petrochemicals, and fine chemicals or other chemicals. And besides chemicals, we really want to also highlight or give a special place to fertilizers, because that's close to the heart. And also, last but not least, we are also active in power and utilities. So we have about almost 80 people now on the payroll in 7 locations, as you can see on the slides around the world. And we provide services around the globe. So everywhere on the whole map, we have been doing projects, or we are currently doing projects as we speak. Next slide, perhaps, Christophe. I can state that IPCOS is unique in the sense that we combine the 3 pillars to make digitalization initiatives successful. What do I mean? Well, technology. On the left there, you see technology. Although we are a technology independent company, I'm proud to say that we know most of the existing technologies and software tools used in the digitalization business in the industry. We have very good partnerships with most of the vendors, the big players in the market, as you can see the logos down there. We also have domain expertise. Since 1995, we have been present in control rooms for the optimization of all kinds of industrial processes around the world. And when you install APC, because that's also one very important activity of IPCOS, you get to know the smallest details about your processes and the business of our customers. And since 1998, we had boots on the ground on the upstream oil and gas platform. So we know how these things work. We understand the language that people in the process industry speak. We combine that with all the technologies which are on the market. And of course, the third pillar is what here it is named data analytics, the glue that brings the technology and the domain expertise together and shapes the solutions are the mathematical methods that our engineers know and use. So as you see, also based on the logos in the middle there, we have done many projects for the big players in the process industry, and we are happy to add you also to that list if you are already not there. Okay, let me first now start introducing our speaker of today, which is Christophe Berks. He's an experienced engineer with a demonstrated history of solving real-world problems in a wide variety of industries. His key strengths are the applications of data analytics, machine learning, software development, and numerical methods. Just to name some of his accomplishments. He developed a data-driven advisory system to support monitoring and maintenance of oil wells. So that's the upstream industry. And in the downstream industry, to just name one, he also developed a cloud-based data-driven platform supporting the optimal operations of chemical production plants. And there are many more, but just to show you a little bit of his experience in the different industries we are active. And also the different approaches that are used, cloud, non-cloud, and so on. So I'm convinced that Christophe is the right person to present this webinar today. So we are all set to start with the presentation. Christophe, the floor is yours.
All right. So today we will be covering a number of factors that determine the success of data analytics projects. We will start at the project definition phase, and then we will cover project feasibility, execution, and finally the organizational model. So you start at the beginning of a data science project, which is your project definition phase. When you define a data science project, like all projects, you need to have a clear business goal. Your goal should never be to just apply data analytics. You need to want to solve a problem where analytics just turns out to be a good solution. You need a goal also that is measurable and quantifiable. For example, you want to reduce the number of bad batches in your process by 50%. This will provide your execution team with a direction and an acceptance criterion. Without it, your project may get stuck in an exploratory phase and it may never deliver a final product. Once you have a clear goal, you compose your team. We've identified the following minimal set of roles that you should have within your team. First up is your project sponsor. The sponsor is the person who wants your data science results. They represent your business interest. Sponsor is responsible for deciding whether your project is a success or a failure. And because of that, during project definition, you need to get clear goals from them, possibly through directed interviews. And once the project is underway, it's critical to keep the sponsor informed of any intermediate successes or failures. Second is the end user. He is a much more hands-on profile. They will provide you with detailed information about the day-to-day work process into which this model will be deployed. They will serve as your domain experts, and because of that, just like the sponsor, you need to keep your end user informed and make sure that your efforts align with their need. If you don't do that, then they just can't or won't use the model that you create, and your project will not deliver any long-term value. Then you have your data scientists, who is a more technical role. They will be responsible for execution steps such as data processing, your statistical tests, applying your machine learning models, and then evaluating their results. But they will also need to set some kind of a project strategy, and they will be responsible for keeping your end user and your sponsor informed. They can also be responsible for project planning, or you may opt for a separate project manager for that. Then you have your data architect or engineer. Their primary job is to prepare the data for the data scientists. They will be building data pipelines that bring together data from different sources in a correct format. Finally, the final crucial role is operations. The operation role is responsible for the product or system in which the final model will be used. They will be supporting your team in deploying your model into production. Depending on your project context, this can be software developers or DevOps experts. Once you've assembled your team, a final step should be some assessment of your technical feasibility. The way we see it, there are three factors that determine a data science project's technical feasibility. These are your process characteristics, model purpose, and your data availability. We'll start with some details on the model purpose. With that, we mean the level of complexity in the analytics that we want to apply. Commonly, 4 levels are identified. First, there's the descriptive analytics. This is the foundation of all data insight. It is the simplest and most common use of data in business. It answers the what happened questions, and it does that by summarizing past data. For example, if you have measurements on a pump, a descriptive analysis would just be to visualize your pump flow, visualize your rotation speeds, and then determine when the pump was down, when there was some kind of failure. The next level is your diagnostic analysis. This takes the output from your descriptive analysis and tries to find the causes of those outcomes. To do so, it tries to find relationships between the different pieces of data you have and to identify patterns. We continue our example with the pumps, then that means you try to look back in time through the time period before each failure, and you determine patterns that regularly occur before a pump failure. This would allow you to classify different types of failures. Next step is the predictive analytics. This tries to answer the question of what is likely to happen. This type of analytics uses your diagnostic results and tries to make predictions about the future. In our example, that means you take your patterns identified and linked to different types of failures, and you use it to describe the condition of your pump and to predict if and when a certain type of failure is going to occur. So descriptive and diagnostic analytics is common practice in business. It's the predictive analytics where a lot of organizations begin to show some signs of difficulty. Then the final level of analytics is prescriptive analytics. This helps to answer questions about what should be done. This goes beyond just predicting your future outcomes, but it wants to suggest actions to influence your future outcomes, and it tries to show the implications of each of your decision options that you have. If we take our pump example to this final step, you end up in a prescriptive maintenance system. This would be constantly monitoring the state of your pumps in a plant and then make real-time recommendations about what the system believes to be the most cost-effective maintenance actions to do. Prescriptive analytics is currently considered state-of-art, and there are very few companies that really have achieved this kind of data-driven decision support. Each of these levels has the potential to deliver increasing values, but because of their increasing complexity, it requires a larger investment in terms of data and resources to achieve. The second factor that determines your project feasibility are your process characteristics. This is the complexity of the system or the process that you are trying to describe. Each of the characteristics that you see here has an impact on the data required to set up a sufficiently accurate model. For example, if you have a system that exhibits a very non-linear behavior, you're going to need sufficient data over a sufficient operating range in order to describe the system properly. On the other hand, if you have a controlled system, it tends to operate in a relatively small operating range, and so you may need less data in order to describe its behavior sufficiently accurate. And then the third factor that links everything together is your data availability. The more ambitious your goal or the more complex your system, the more data you will need. And we're not just talking about the raw amount of data here. You need to remember that data-driven models cannot extrapolate. So you need data that describes the full operating range of whatever system that you want to model. Example is you want to model a time variant system, and you will need data points across the full lifetime of your system. You may also need data from multiple sources, combining real-time measurements with tabular data from the lab or from maintenance. If you look at the prescriptive maintenance system that I just mentioned, you would need both real-time measurements as well as logs of your repair times and your repair costs. You would need to combine that data in order to generate your optimal maintenance plans. To summarize, in order for a project to be technically feasible, these three factors need to be properly imbalanced. Something we see a lot is requests from clients where this was not the case, and that means your project is just infeasible from the start. This usually happens because there is a lack of understanding that there are still limitations to what data analytics can do. You can see some examples here of common project requests. So the top two are currently state-of-art and state of practice and state-of-art use cases. We know that they are doable as long as you have the required real-time data. The anomaly detection is state of practice, very easy, relatively easy to do. Batch conversion estimation is something that you can do if you have required data. In the bottom two cases, data-driven models will struggle because of insufficient data to describe the complex model, or the too high ambitions that combined with a very complex model. Those are the two bottom cases. So, next step, once you've defined a business goal, you've assembled a team, and you've done some assessment of your technical feasibility, project execution will start. What we see in a lot of companies is that a data science project is treated like it's a software development project. And thus they try to apply the most common methodology, which is Scrum, to its execution. Scrum works very well in software development, but applying it directly to data science does not work well. Reason for this is the fact that data science is very nonlinear and iterative. You can see this in the picture to the right, which is called the CRISP-DM model. It's a standard process that describes the steps involved in data science work. As you can see here, there are a lot of cycles in here between, for example, your data preparation and your modeling. And these cycles indicate that data science is highly exploratory, and it involves a lot of experimenting with different feature sets, different model types, and so on. This results in a lot of uncertainty, and Scrum is just unable to handle this very well. However, that doesn't mean that the Agile guidelines on which Scrum is based cannot be valuable for data scientists. Agile is just a set of guidelines focusing on efficient communication with stakeholders and within your team. It focuses on providing intermediate results for testing and then adjusting to whatever feedback you get from your stakeholders. This can work and is very valuable to try and do within a data science project. An approach that we've seen work splits the work that within a data science project in two parts: your exploration side and then your product development. And then each applies their own agile methodology. We'll show one specific use case to try and explain this a bit more. So this shows the team composition in one specific project where we were involved. There were two teams defined, each using their own agile approach. You had your research team, which focuses on experimentation, meaning your data exploration, feature engineering, model training, and validation. And then you had the development team, which focused on integrating the resulting models into a final product. This approach was done here because it was a new product that was being developed, so they needed an active development team working here. Now, these teams, they worked separately, but they had to be aligned in some way. And that was done by sharing a product owner. The product owner made sure that both teams were always focusing on providing value for the assets, and that both of those teams gave updates back to the assets. So this transparency was very important. Then they also shared the Scrum Master, which directed the teams. The Scrum Master made sure that the research team had sufficient freedom to experiment, but they still had to deliver at a sufficient pace, so the development team always had something to work with. And then the final link between the teams was a domain expert with some machine learning experience, who provided domain knowledge to both teams and helped the development team in integrating the models. The product development team was did software development work, and so they worked according to the standard Scrum framework. So with daily Scrums, and every 2 to 3 weeks, you had a product increment. Their job was to incorporate the deliverables of the research team into this product. The research team worked in its own independent development cycle, but they followed a more relaxed version of the Scrum framework, tailored more towards data science work. For example, they reduced the number of stand-ups and they made iteration timings a lot more flexible. Biggest challenge in this approach are those deliverables, the model increments. These need to be at least one step ahead of the development team so they never run out of work. These model increments, what are these? Well, they can be additional features that are added to a model, but also extending the range of systems that are modeled or incorporating additional data sources. And for each of those model increments, the research team had to go through a full cycle of data processing, model training, and model validation. Research team also retained responsibility of every model that they delivered. This is done to encourage that they deliver reliable and validated models. So, in order to build reliable models, the guidelines that we follow is to always keep model complexity to a minimum. This comes down to finding the simplest model that properly describes your data without underfitting or overfitting. What we do is we always do a literature review when starting a project to see if anyone else has worked on anything similar. And then we do a proper model type exploration, and hyperparameter optimizations are also always done. If you're going to do those, you always need to make sure that you have some training, test, and validation split of your data to make sure that you're not overfitting through your model type exploration or hyperparameter tuning. We also try to incorporate feature engineering a lot because this allows you to incorporate the domain knowledge into your process. This often ends up reducing the complexity of the model that you need in order to properly describe your data. For example, we had a case where we could classify our data using a multi-layered neural network, but by applying proper feature engineering, we could get the same performance using a much simpler decision tree based model, and we preferred that over the neural network. So yes, we did move away from a deep neural network in that project in favor of decision trees. This is because while true that deep learning neural networks have made tremendous achievements, applying it to a new use case actually requires a huge investment in terms of data, in terms of computing power, and in terms of manpower to get a well-performing network. This is because the work done around deep learning focused a lot on a number of standard use cases, such as speech recognition, translation, object detection in images, and so on. And this has resulted in several deep neural network structures, like the one that you see at the bottom here, that work very well for those specific cases. But this doesn't really transfer very well to new use cases. So if your project goal aligns well with one of those standard cases, then yes, deep neural networks combined possibly with transfer learning is a valid option. We did that in a very simple case where we had to do image processing to detect if people in a plant were always wearing a helmet. That aligns very well with object detection within images. But if your use case is more unique, it is probably a good idea to first investigate the simpler model types and only turn to deep learning when nothing else works, just because of the sheer model complexity and the investment needed to get this to work. Once you've built your model, you need to prove that it works. In a lot of projects that we see, this just means someone evaluates the model against the test data set and then reports on its accuracy. But accuracy is actually a terrible metric to use in a lot of industrial cases because it doesn't deal properly with imbalanced data sets or the fact that there are uneven consequences to false positives or false negatives. To give an example, if you have a system that detects failures in any machine, and you fail to detect that your pump is going to go down or your machine is going to go down, that can have very high costs. While generating a number of false positives just generates a bit more work, and the cost is a lot lower. If you're evaluating a model purely based on accuracy, you're not taking into account these so-called uneven consequences. In this case, what you actually want to use are metrics such as recall and precision, or even create a plot like this at the top, which shows you the trade-off between these two metrics, and then you can find your optimal point on this curve for your model. Another step that we are starting to see more and more, and that is very useful, is the use of model interpretation techniques. These are techniques that try to explain the behavior of a model, because most models are black box and you don't understand what is going on internally. So using model interpretation techniques, you try to explain this behavior. For example, what you see here is when you try to show the contribution of each input feature to a single decision that was made. Using this kind of techniques allows your data scientists to debug models during training, and also to explain the decisions made by the model when it's running in production. And you can explain the decisions that it makes to your stakeholders. So applying these guidelines on reliable models and model evaluation and interpretation will help you build proper models that you can deploy into your product. Important thing to remember, though, is that once your model is deployed, the work is not done. It's never truly done. Over time, any data-driven model's performance will start to degrade. This can be due to a variety of reasons. The first reason is generalization, meaning the model saw an input that was not in its original training data, and its response was unexpected. A second reason that can occur is called data drift, meaning that the distributions of the input variables change over time. This can be due to environmental factors. And a third reason is concept drift, where it's actually the interpretation of the output variables that changes over time. A good example of that is you have a batch monitoring system, and the limits to what constitutes a good batch or a bad batch evolve over time, but then your model will start to become less and less reliable because it was trained on the original rules of what makes a good or a bad batch. So to deal with model degradation, you always need to have a model monitoring and a model update strategy in place. An example model monitoring and update strategy we have implemented was the following. We created a condition monitoring system for linear displacement pumps. These pumps cyclically move up and down, and throughout this movement, your load varies. If you plot this behavior, you can get the figures like the ones on the right. We created a system to analyze those measurements and then classify them to try and detect the current state of or the current condition of the pump. In our final product, we integrated a reporting system so that our end users could report whenever they encountered a misclassification. And then whenever we received a certain number of misclassification reports, we triggered a retraining procedure. In our retraining procedure, we first let a domain expert review these reports to make, and any report that he agreed with or was added to our data set that we use for model training. Then we have a step where we update the weights of all of our training data so that we give more weight to more recent data points, more recent measurements. And then with this new data set and its new weights, we retrain our model, and then we check if its performance based on an F measure is sufficiently high. If so, we replace the existing model. So it's important to remember that model degradation means that a data science project is never truly done. You need to have some kind of long-term maintenance system in place. This is crucial for your project to deliver long-term value. So that's all that we have right now on project execution challenges and guidelines in that. Our last section is a bit more high level. We look at how data scientist teams can be positioned within a company. These teams can consist of any number of people that are formally trained as data scientists and that cooperate on one or more projects. We'll start with the two extremes, which are the decentralized model and the centralized model. In a decentralized model, you have each business unit that hires its own data scientists and they execute projects that very closely align with the requirements of that business unit. This often happens in companies when data science expertise has appeared organically and it was not centrally organized. Resulting projects often have a very high buy-in because of stakeholder connection and business proximity. So these data science teams, they are really part of the business that they need to support. However, there's a lack of any central guidance in this model, and there's no knowledge sharing. And this may result in duplicate work across the different data science teams. You may have duplicate infrastructure, and you have a complete lack of any standardization. This will give you higher costs. And these teams will end up having knowledge silos because they don't really share the knowledge and experience that they build up over their projects. If you want to counteract this, then you need to have some kind of a data science support network within your among your teams so that you connect the different teams with one another and enable them to discuss on what projects they have done, what their the learnings and the challenges that they faced. Second model is the centralized structure, where all the data scientists within a company report into a single head of data science. For example, your chief data officer. In this structure, data scientists will have more opportunities to participate in a wider variety of projects. They can collaborate with their peers, and therefore you have better career growth, technical mentoring, and so on. This also allows you to set up company-wide analytical initiatives, meaning you will not have any knowledge silos. The biggest downside is that your analytics team can be very far removed from the business that they actually have to support. This will lead to problems in buy-in from the plants or business units for which the projects are executed, and low adoption of your final results. So if you have a centralized model, you need to actively work to build a relationship with the staff of your plants or the business units that you want to support. And you need to make sure that you have sufficient domain knowledge as you develop your solutions. Outside of startups, very few companies are actually purely decentralized or centralized. Most have some kind of hybrid form where they decide that some responsibilities need to be centralized, but some can also be delegated to the business units. There are two common forms there. One is the hub and spoke model, where you have a centralized center of excellence that's responsible for what the best practices are, building your data science culture throughout your organization, and addressing any cross organizational challenges. At the same time, within this model, you then embed data scientists strategically in high value business units to work on specific operational challenges. This approach tries to find the best of both worlds, but it can be more costly and it requires significant coordination and, most importantly, agreement from everyone involved on what the responsibilities are of your center of excellence and your embedded data scientists. And then a final approach that we see gaining more and more traction is based on data democratization. Here we still have a centralized team that has expertise about data science. But instead of embedding data scientists, you try to empower your local teams to support data science projects. So people who are not formally trained to be data scientists. By empowering, we mean that you have to educate them in analytics. You need to provide them with access to all of the relevant data, and you need to provide them with the necessary tools to easily perform analysis on their own. This is the basis of what is called self-service analytics tools, such as Trend Miner and Seek. They're very common examples of this. The result will be that your local teams have a maximized buy-in and ownership of your data science projects and their results. You just need to keep in mind that you're providing data access to a lot more people, which creates risks in terms of data corruption, security, and privacy. So there are a lot of different models. There is no one organizational model that works best. Each has its pros and cons. What's important is that you know which model that you are in and that you actively work to minimize the downside of this model, because that may have an impact on your work. So that was it for this presentation. To conclude, if you want to maximize the odds of success for a data science project, you need to start from defining a clear and measurable business goal. You need to make sure that you do an assessment of its technical feasibility, balancing your model purpose, data availability, and your process complexity. You want to apply agile principles during execution, and you need to be aware of the organizational model that you're in and what its impact can be on your projects. Thank you. That was it. We will now go to the Q&A.
Yeah. So many thanks, Christophe, for the nice presentation.